Hello. I'm gonna recap on the stuff I talked about stress and strain and Young's modulus from the last lecture, and take it a little further. What I covered in the last lecture was the essential stuff that we need, in particular for our Dow's tests. This one takes that information that you had in your lecture, and we go a little bit further with it. Okay. So the main form of stress that we're interested in is normal direct stress, and we will be looking at normal direct stress, and later on in the course we'll be doing bending stress. We ought to mention shear stress because it does come up conceptually, an important concept, but in terms of your Taoist and your exam, the majority the stress that we need to be interested in is the normal and the shear stress. So stress, whatever form it might come in, is going to be basically a force divided by an area, and how that force is related to the area, it depends on the kind of type of stress we've got. In the case of normal stress, it's the force that is normal to the area that you're of consideration that's been pulled apart. So it's a way to measure the intensity of a force independent of its geometry, really. So if I have a thick cable I'm trying to pull apart, I can apply a lot of force there, and it will break. Alright. Now if I have a thin cable, how much force do I need to apply to pull that cable apart? Well, obviously not so much. I mean, we've all experienced that. So we can have the same material and different amount of forces are required to pull it apart. However, we'll find that the stress is not independent of that material, pretty much. So the stress is a better way to look at whether something's going to get pulled apart and how much it's going to get pulled apart, how much elongation there's going to be. So it's an important way to measure the amount of load we're applying to the structure. The symbol that we are going to use for normal stress is sigma. Okay. For shear stress we tend to use the symbol lowercase tau. But they're both stresses. So for direct stress or normal stress, or even it's known as uniaxial stress, we've got a bar here, and we're trying to pull it apart, and we're going to measure how much stress there is somewhere inside the bar. We're going to take this cross-sectional area, so it's orthogonal to the direction that we're trying to pull, and we're going to measure how much we're measuring in effect the stress in this area here. Okay, so we've got a force divided by this area, and that tells me the stress. This particular case, you can see it's in tension because we're trying to pull the bar apart. The forces are pulling outwards. So I can do an imaginary cut inside the bar, and now we can just look at the bottom section. So we're doing in effect a method of joints or a method of sections in this bar. We're cutting through it and imagining what we can see in terms of the internal force inside. And inside we can see this internal stress, which is counterbalancing this external force being applied. Again, looking just at the bottom half, we're imagining we're going to cut the beam in half, and this time I'm going to imagine I'm going to try and squash my beam either side. So I'm only looking at the bottom half of my beam, and so therefore in that case my stress must be pointing in the opposite direction against the force where I'm trying to squash it so that this whole thing isn't going to move. So my internal stress in this case appears to be acting as if it's going towards the compression force that's been applied from the outside. So the stress is going to be the, in this case, it's going to be the average of the force divided by the cross-sectional area. Notice that we're using the internal resultant force here. So we get into this argument about what is stress and what is true stress and engineering stress and so on. So the fact that when I start pulling things apart, my cross-sectional area changes. So you can define stress therefore in two ways. You could define stress in what's called true stress, where we're measuring the actual area that we can see inside our component that we're trying to pull apart, and we're taking into account the fact that the area has changed. And then there's the engineering stress, where we assume that we'll take the original area of our member. But we don't need to go into those details. They're more of a stress level 2 concept. So stress is going to be the force divided by the area. So normal units we're going to use is newtons divided by meters squared. And it happens to be that newtons divided by meters squared is also a Pascal. So it predates the formal definition of Pascal, at least in English engineering textbooks, and so using Pascal as a stress unit is acceptable, certainly in terms of English textbooks. European textbooks, you might argue that Pascal should only really be used for pressure, but I can't remember the dates exactly, but there's 30 years usage of Pascals as a stress unit in English engineering, at least. Now Pascal is a very small unit in terms of atmospheric pressure, for example. The pressure that we are being exerted upon by the atmosphere on ground level is about 101,000 pascals. So that's an awful lot of pascals. So we are going to be normally, when we're pulling bars apart and that sort of thing, we're going to be working in the millions and possibly even the billions. So often we will use megapascals, because that's the typical sort of value where you're going to get metals being pulled apart, so you're not going to go values beyond that. So we will typically be stating our stress values in megapascal terms, and that relates to 10 to the power of 6 newtons per meter squared. So that's what 1 megapascal equals. And a lot of engineers don't like using mega, so they use newtons per millimeter squared, okay? Because what we got there, so 1 meter squared is going to be 1 million millimeters squared. Okay. So just emphasizing this point that stress can be quoted in different units. It's quite common to see engineers quote stress in terms of newtons per millimeter squared instead of using newtons meters squared. That's quite a common thing you see in engineering design and stuff. Now don't forget, why is it going to be 1 million millimeters squared is equal to 1 meter squared? Well, we have to go back to the fact that you have 1,000 millimeters in a meter. So if I'm going to square my meter, I've got 1 times 1. So let's square my millimeters. So then I've got 1,000 millimeters times 1,000 millimeters. So 1,000 times 1,000 equals 1,000,000 millimeters squared. So that's a trap that people often fall into, that when they go from 1 meter squared to millimeters squared, they tend to just do this conversion here, which is wrong, so I don't even want to say it. So you've got to remember, you've got to multiply your 1,000 2 times, okay, or square it rather. Here's an example I did in the lecture where we got a direct stress on a bar. Now if you see just the word diameter, you can assume that it's referring to a cylindrical bar. So we've got 20 meter diameter steel bar which is loaded with 10,000 newtons. The stress in this case is going to be 10,000 divided by the area. Okay, this is my weird pi symbol. So I've got 10,000 divided by pi d squared divided by 4. Notice it's far better in fluid mechanics and also stress analysis. If you're given things in terms of the bar's diameter or the tube's diameter, to stick using diameter and use this formula and not pi r squared. Use pi d squared divided by 4 for your area. You're less likely to make a mistake then. So I'm going to substitute those numbers in, and then I end up with a stress of 31.38 times 10 to the 6 newtons per meter squared. And so we'll drop this and we'll drop it down to be in meganewtons per meter squared. So that's my stress value. Okay, this is an example now where we're going to be in compression, and we use now a square bar, so a 10 by 10 milliliter bar, and we've loaded it now to a 20 kilonewton value. So we've got force divided by the area. Now this time, because it's in compression, I'm going to take that into account. So what I'm going to do is, for my definition, I know that when I apply a external force, and if my external force is in compression, my internal force should be negative. So I'm going to say minus 20,000 there. Okay, so that's where the minus is coming from. So if I'm dealing with compression, I'm going to use this notation of minus 20,000. The area is this time easy to calculate. It's just 0.01 times 0.01. Okay, so let's work that out. Straightforward. We could dump all this straight into our calculator, this previous line. And then we're going to end up with a result of minus 200 times 10 to the 6, which is in units newtons meter squared. And then I could finally restate this in terms of megapascals or meganewtons per meter squared. So minus 200 megapascals. And I could also highlight, this is not considered a double negative. This is what you should do. So even though we have minus here, we can also tell the reader that we know that this is in compression. And so we could highlight that to the reader that it's in compression. Now for strain, that's when I'm applying the stress and I'm going to expect to get some extension. Okay, so I'm pulling it apart and I'm expecting my bar to be moving a certain extension, which is my delta L term here. So that's how far it's extended. So the strain can be defined as the change in dimension in, let's say, in the x direction divided by the original length. And so that's my definition for strain. So change in length divided by the original length. So this is a way to measure in a relative form how much the material has elongated. So I'm going to say relative, or we could say it's in effect it's almost like doing a percentage change, isn't it? So if I have a small bar, not very long, and I try to pull it apart by a certain amount of stress, that can only extend a certain amount. Or if I have a long bar, I've got more material that I'm trying to stretch apart, so therefore I would expect a longer elongation. So again, trying to get rid of the effects of geometry here, that's what we're trying to achieve. We can say, let's look at the strain that's happening. Okay, so for my small bar with the small elongation and its small length, it's divide that, the elongation divided by the original length, compare it to the long bar, which has a longer, it's going to have a longer elongation because it's got more material that you can pull apart, divided by its original length, you're going to get the same values. Okay, so we've taken away, if you like, the effects of geometry on our problem. In terms of units, strain is dimensionless, so it has no units. However, some you'll see in engineering documents and things like this, you might see people writing out the units in terms of meter stroke meter or millimeter stroke millimeter, and some textbooks will use percentage as well, so they times the answer by 100 and they will state percentage. So the reason why you'll find that in some textbooks is basically you're highlighting to the reader that you appreciate that there aren't any units. What some people can also do is, we're using this millimeter stroke millimeter idea, is can be telling the reader that you measured the original quantities in terms of millimeters. So that's why some people might do millimeters per millimeter and some people might do meters per meter. So it depends. The symbol that we use for strain is epsilon, so that's kind of the Greek E, I think it is, isn't it? So engineering materials do not stretch much under load. So when we're building our bridges and so on, we're not expecting great strains. So the values of strains ratio, so how much elongation I've got compared to my original length, is going to be down into like I don't know, about 1 times 10 to the minus 6. They will be typical strain values that we'll be working towards, up to about 1 times 10 to the minus 4. So if I looked at these values in terms of 1 times 10 to the minus 6, you can see we're for most engineering designs we are dealing with numbers from 1 to about 100 times 10 to the minus 6. These are the sort of typical strain values you'd get in a structure. So because 10 to the minus 6 is so typical for a engineering structure that you could be looking at, we're going to often get rid of this and use the symbol micro strain. So micro strain will either be represented as a mu epsilon, and also other authors might just drop that down to a mu. So mu representing that we know that we're dealing with 10 to the minus 6, or mu epsilon representing that we're dealing with 10 to the minus 6 and that I'm telling you that it's a strain value. So this is a good sort of symbol to use for when you're quoting your strain values, this mu epsilon term. So here I have did this problem, got it wrong in the lecture. Okay, so okay, the stress of a lecture. Okay, so we've got 1.2 meters long bar, and we've got an extension of 1 millimeter. So what I want to do there is either convert my millimeter into meters or my meters into millimeters and then divide by 1 by the other. It probably makes more sense to convert your meters into millimeters because then we're dealing with whole numbers. So that's what we've done here. So we've got a change in 1 millimeter divided by the original length of the bar, which is going to be 1,200 millimeters. So divide those numbers, put them in your calculator, and then you can, on your calculator, you can press the eng button, and usually that will bring up the 10 to the minus 6 there. So we can rewrite this as 883 microstrains. Okay, so let's talk about shear stress, although it won't be coming up in your Taoist tests, and I don't think it's likely to be in the exam. So the shear stress is another form of stress where we're getting this shearing action. So it's good to introduce because we're going to move on next to doing shear force diagrams. So this at least introduced this idea of a V for shear force. Okay, so this V here is F basically. It's my force being applied to this block, and we've got this, so it's parallel to the block. This is my area, and so if I take the force, so that's my V, divide it by my A, I'm going to get a stress value, and this type of stress value is called a shear stress value. The symbol for that typically, not always, but typically is tau. And so sometimes different textbooks like to use different values for force. So sometimes, for example, you might have F for just a regular kind of force. In this case, we're going to use V for a shear force. Then there's I've seen L for a load force, also P for a pulling force, and so on and so forth. So some textbooks try to be a bit more specific in their symbols that they're using for force. Okay, and R, of course, is a reaction force. Okay, so again, it's the intensity of the force that we're applying per unit area, where the force is now going to be tangent to the area, so it's going to be parallel to the area that you're trying to pull. So you've got to imagine that we're trying to slide this area off in this direction, and this area is now kind of glued, for example, to a surface and it's not moving. So what happens if we apply a force along here? Okay, now notice in this diagram we've changed it to a pulling force. So we have applied here to a force here, and we've glued the bottom bit. What will happen? Well, we would expect this to shift a little bit to the right. So it's going to shift a certain distance x to the right, and it will have a certain height. So x divided by L is going to be my definition for shear strain. Okay, so shear strain. Notice there's something interesting about shear strain, which is that if you were working in radians, your shear strain and your this only works for radians, by the way, and your angle, if we consider this to be an actual angle, are the same values. You could try it in your calculator. Try setting your calculator to be try setting your calculator to be in radians, and type in your calculator 0.1, and then type in your calculator tan 0.1. So that's the opposite. So that's my 0.1, and this is my height. That's my 1 meter, say. So you find that you get a very similar number. So the ratio of these lengths and tan of these values is the same. It's called the small angle theorem. So we are not going to do much in terms of the Poisson's ratio in terms of assessment, but it's a good thing to introduce and to know about. So we've all seen this. If you imagine, say, a rubber elastic band, you can quite easily see the Poisson's ratio in action. Well, you take a nice thick rubber band, start pulling it apart, and you notice it gets thinner and thinner. Well, the same thing happens for metals, but it's very difficult to notice because the amount of force that you need to pull a metal apart to notice this effect is extreme, and the amount of deformation that you get from a metal is not as large as for rubber. So that relates back to the Young's modulus. So this effect is measured by Poisson's ratio, and Poisson discovered if you took the lateral strain, so imagine that I'm pulling this thing apart in the y direction. So that's my longitudinal strain in this particular case. So I'm pulling it apart. So that's my longitudinal strain. What happens is that the lateral strain, which is in the x direction here, will move in a little bit, and the amount that it moves in is not typically the amount that we would have to keep the total volume the same. So when I pull this apart in the y direction, it moves in a little bit, but not typically to match the initial volume. Okay. If it did, actually, the Poisson's ratio would be equal to 0.5. But for most materials, we get values below 0.5. So we get values of 0.45 for rubber. So when I pull rubber apart, typically the volume stays pretty much the same. So you get quite values heading off to the 0.5 value that I'm talking about. Whereas for metals, this effect, if you like, loses its volume a bit more significantly, and for most metals we have a Poisson's ratio of 0.3. So why 0.5 would give you the fact that that thing that I'm pulling apart would keep its volume? Well, let's think what's happening. Now, let's not consider this to be just a 2D shape, but a 3D shape. So if this was a 3D block, what would happen if I'm pulling it apart? Well, 0.5 of it would go in the y direction, but now if we look at it in terms of 3D, as a 3D block, 0.5 will be going, if you imagine, out of the page into the page, so in the z direction. So that's why we're getting 0.5. So we're getting 50% of it would be moving in from, in my particular case, x, the x direction, and 50% of it being moving in from the z direction, which we can't see because it's coming out of plane. So that explains why we have that 0.5 figure. So what's important with the Poisson's ratio is the fact that we're using the ratio of strains. So this wouldn't work for if we were using some sort of like the ratio of elongations. So that wouldn't be for one type of material and another type of material. We would get different Poisson ratios if we measured it like that. So that's why it's a good reason to use strain, because strain gets rid of any geometrical effects. Okay. Now the other thing that's interesting about the Poisson's ratio is that we use a minus. So I'm pulling it apart, and what's going to happen? So I'm going to get an extension. So I'm going to get a positive. Pulling apart here. So I'm pulling apart in my y direction here. So I'm going to get a positive y as it gets pulled apart. Now x moves inwards. So x is it's not elongating, but it's contracting, as it were. So we're given a negative value. So we've got negative value divided by positive value. So Poisson decided to put a minus in front so that we'd end up with Poisson ratios that were positive. Okay. Okay, so let's come back to stress and strain now. So where we're interested in is where Hooke's law is being obeyed. So you've probably all come across Hooke's law, where the force, if you apply greater force, you get greater extension. So when you see stress, imagine that you're seeing force there. So that's my force. And where you see strain, imagine you're seeing elongation there. And that's my elongation. And remember that stress is the way to look at force. We're getting rid of the effects of geometry. So we're doing force divided by area. Strain is a way to look at elongation, again getting rid of the effects of geometry. So what happens is that if we plot a stress strain plot for a piece of rubber that's kind of quite short and we're trying to pull it apart, we will find that if we compare that to another experiment where we repeat with the same material but a longer piece of material, we end up with the same stress strain plot. That's why we're going to look at materials in terms of their stress strain plots. And more force being applied, more extension, and it happens that we get a fairly linear growth for most materials. So that linear ratio is going to give me a gradient, and we're going to call this gradient Young's modulus, also known as the modulus of elasticity. Okay, or Young's modulus for elasticity. So it will be quoted in books like that: Young's modulus of elasticity, elastic modulus. So those terms all mean the same thing. It has units of newtons per meter squared because we are using stress divided by a non-dimensional term here. Okay. A related term is modulus of rigidity, which is G, and this is the same thing but now for what would happen if we are looking at the shear stress. So if I try to twist my rod or whatever, and I'm measuring how much shear I'm going to get on the outside of my rod divided by how much strain that I'm going to get, you can use this as a modulus of rigidity. We're going to come back to this term later on, I think pretty much maybe lecture 10 or so. So let's not worry about this too much now. The ultimate tensile stress is the stress which we can assume that things are going badly wrong. So we're starting to go way beyond our limit where we're going to get a linear relationship. So this linear relationship works up to the yield stress position, and the ultimate tensile stress, you can consider that to be the maximum amount of stress that you can apply, at which point you would not design anything at all. So because this is the largest amount of stress that a sample can take, most structural engineers will be using this as the value that they're going to measure the factor of safety. So we're going to be using the ultimate tensile stress as a means for factor of safety. I should point out that different types of engineers do use different stress values here. So it might not necessarily be the ultimate tensile stress that we are going to measure factor of safety, but we for our module will take to use that term for measuring factors of safety. So what we need to do is find the largest stress that my component can experience and divide it by the amount of stress I'm planning to apply to my component. So maximum that it can do divided by the amount that I'm planning to apply. So notice that should be a number that's more than 1. Okay, if I'm applying to apply more stress than the material can actually experience, then it's going to fail in some way. So my factor of safety must always be more than 1. However, we probably don't want to design things crazily high values, because if we're going to design crazily high values, then what we're doing there is we're using lots of money to build something that's what's called over-engineered. So it's we're using stuff which is unnecessarily, okay, which also might in itself cause engineering problems. Not just the fact that we've spent too much on using too much materials. If we use too low values, then we can predict that we might have problems. We might, so that's not a great idea. And also, we're not doing fatigue analysis or anything like that in this module, but if we can imagine that we are going to get repeated loads, cyclical loads, then you get these things called fatigue, stress, and things like this. And so you want to be well above, have a factor of safety well above 1, so that these factors which are going to kick in for lower values of factor of safety. So the reason why you want to have a reasonably high factor of safety is because although you tell the company who you've built the bridge for, yeah, this bridge should take 5 cars on it, but they decide, okay, nah, let's put another car in it and get some more money. So the operator might not load your structure how you've designed it for. Then in particular for welding and issues like that, you can get defects, local stress rises in the structure, so then you have to counterbalance them, so over design a little bit to take in the facts that the manufacturer in terms of welding, in terms of cutting, in terms of bolting can cause local stress rises, they're called. Then the materials that we get supplied, well, they might not be as good as the manufacturers promised them to be, so we'll have to take that into account. Then we need to take into account that when we put the structure out in the environment, due to corrosion and wear, things aren't going to be as strong as they were as they start corroding or somehow getting worn out. There could be an accident as well, so something might get scraped by accident. Some slight damage might occur, so we might want to take that into account for our factor safety. And then there's this issue of fatigue and whatnot. So we have stresses which we are assuming that stresses are being applied slowly, and we're assuming they're not being applied repeatedly. And so these if we suddenly apply the stress, there's going to be associated acceleration there, so an associated impulse or force would be associated, which would mean that we would get higher forces being applied than we expect, and a repeated application of force can lead to fatigue issues. Okay, so if we go too high, however, we are going to then end up using a lot more material than we expect. So that's going to cost us money, and it's also going to cost us weight. So in particular for an airplane, that's going to be an issue. For a bridge, I suppose, not so much of a big issue. And any other form of machinery, again, we don't want to over have a over high factor of safety, particularly because there's going to be, again, issues of fuel efficiency and operating costs. So these are quite high values in terms of engineering design, but yeah, a factor of safety of 1.5 going up to say 3 for steel, for cast iron 2 up to 4 for cast iron, and how cast iron is being used. It's not doesn't behave very well in tension. Timber could be going from factors of 2 up to 7, say. The timber has effect of seasoning, so if you use green wood, it can absorb quite a lot of energy from damage, but it's not as strong, or it's not as stiff. Whereas if you use hard seasoned wood, it behaves a bit more like a bit more like a cast iron, really. So you ideally, however, although we've mentioned the fact that we are going to measure our factor of safety in terms of the ultimate tensile stress, which is our highest stress value that we can experience, the other stress value that I mentioned, which relates to the elastic limit, which is the yield stress, and it's really up to the yield stress that you want to design anything for. So that's a lower stress value. We will use the convention that if something is experiencing a positive load, so if okay, let's rephrase this. So if we are applying a load to something, then we're going to say that that load is in the sense that I've got a load hanging off a bar, then that is going to lead to something in tension. And if I'm putting a load, a negative load, so that's what I'm saying there is I've put a load on top, that will lead to a compression. So that's just some terminology. Okay, let's go to this example where we're using the relationship of Young's modulus is stress over strain. So we've got the extension so we've got strain is extension divided by the original length. So in my bar problem here, I've got a 1 meter bar and an extension of 1 millimeter. So we've got 1 millimeter divided by 1000. So I'm going to express this in terms of strain, in terms of micro strain here. So I've got 1000 times 10 to the minus 6. The Young's modulus relationship gives me that stress divided by strain. The stress is 200 times 10 to the 6, and the strain is 1000 times 10 to the minus 6. Put that in your calculator and you end up with the answer of 200 times 10 to the 9. So the Young's modulus we've found in this case is there's a typo there. So 100 giganewtons per meter squared. So that's 200 giganewtons per meter squared. So that's 200 gigapascals. Sorry for that typo. Here we are looking at a problem where you've got a 2 meter long bar. It's stretched by 1 millimeter. And it has a stress of 63.66 megapascals. Can you work out what the Young's modulus is for this problem? Well, let's work out what the strain is first. So let's take the 1 millimeter extension and divide it by the length of the bar. So we've got 1 divided by 2000 millimeters. So I've changed my 2 meters into 2000 millimeters. That works out to be 500 micro strain. Okay, now let's go to our formula for Young's modulus, which is stress. Young's modulus is stress over strain. Okay, so we know what the stress is. We know what the strain is. Can we work out therefore what the Young's modulus is? So our stress is from the question, so we've got that from the question, 63.66 times 10 to the 6. And now let's divide it by the strain, 500 times 10 to the minus 6. And then we have 127 times 10 to the 9. So 127 giganewtons per meter squared. Okay, that's the end of my slideshow. So that's taking what we did in the lecture, and we've gone a bit further. Don't panic too much about some of these terms, because I did all the essential stuff in the lecture. So the essential stuff that you need to know is what's the definition of direct stress, what's the definition of direct strain, and that Young's modulus is stress over strain. So they are the three essential equations that you need to know, okay, for your Taoist test.